Okay, so it looks like we have a question from Rachel. Could you do number 10 from lecture 28? Absolutely. Let me get that up real quick. Okay. Let's see. 8, number 10. Okay, so what we're supposed to do is we're supposed to find the first, excuse me, the first 6 non-zero terms in the power series expansion, or this differential equation. All right, let's get to it. So the equation we have here is y double prime plus xy prime plus y, and then on the other side we have this polynomial. So it's x squared plus 3x plus 5. And we want to figure out the coefficients of this, of the Taylor series solution of this polynomial. Now, this is one where they don't give any initial conditions. So unfortunately, we're going to have an A0 and an A1, or undetermined coefficient, or constants in our problem. And it's always the case that y of 0, and we're setting this around 0, is A0, and y prime of 0 is going to be A1. So we automatically know that we're going to have those in our solution. Now, the way we get the next few coefficients is by isolating for the highest derivative, and then we start plugging in numbers and see what that ends up being. So what I'm going to do is I'm going to solve this equation for y double prime, and that just requires some subtraction. So y double prime is x squared plus 3x plus 5 minus xy prime minus y, right there. So now all I need to do is I just need to plug in 0 in for everything and then see what y double prime is going to end up being. So if I do that, let's see, well, 0 into these two will just be 0. So I get a 5 from here. This is x right here will be 0. And then y of 0, that's A0. So y double prime is 5 minus A0. Now remember, y double prime isn't the same thing as A2. A2 is y double prime divided by 2 factorial. And that's probably one of the most common mistakes you can make with one of these problems, is by forgetting to divide by the relevant factorial when you solve for a derivative. So don't forget to divide by a factorial here. That means that A2 is going to be y double prime divided by 2 factorial, or 2. So that's 5 halves minus A naught over 2. That's going to be our A naught here. So let's kind of keep track of the terms we have so far. So we're going to have some that are next to A naught, some that are next to A1, and it also seems like we're going to have some terms that are just on their own as well. So far we have y. Let's see, we have A naught, and the A naught term is always times a constant, so I guess it's just going to be times 1. And then we also have A1 down here, and since that's next to y prime, it's going to be next to an x. Now for A2, we have negative 1/2 A naught, so it's going to be minus 1/2. And since it was a double prime, we have x squared for that. And then we have just this 5 halves on its own, so we're going to have plus 5 halves x squared. So it looks like we have 1, 2, 3, 4 non-zero terms so far, so we need to get 2 more. So that requires us to get to y triple prime. So y triple prime, we can get that from y double prime by just taking the derivative. So I'm going to get rid of this stuff now. So what I'm going to do is I'm just going to take the derivative of this stuff right here. So y triple prime, the derivative of x squared is 2x. The derivative of 3x is 3. The derivative of 5 is 0. And then for this one, we need to do a product rule here. We have minus y prime minus x y double prime when we do that product rule. And then we do the derivative of negative y, which is negative y prime right there. All right, so now that we have that, we can end up getting y triple prime of 0. So if I plug in 0 for everything, well, we get 0 for this. We get 3 here. It actually turns out we have 2 of these y primes. We have minus 2 A1, and then we have minus x times y double prime. But remember, x was equal to 0. So anything that has an x in it, we'll just go to 0. So it looks like our y triple prime is going to be 3 minus 2a1. But once again, remember, y triple prime isn't exactly what we're after. We're after a3, which is y triple prime divided by 3 factorial, or 6. So what we're going to do is we're just going to divide this by 6, and that means that we have a3 is 1/2 minus 1/3 a1. So since we have a 1/2 on its own, we're going to have a 1/2 x cubed like that, and then we're going to have a minus 1/3 a1. So we have minus 1/3 x cubed in here. And now it actually seems like we have 6 non-zero terms, 1, 2, 3, 4, 5, 6. So that means we're finished with this one. So we can pick out the answer that matches this one. So whenever they want, the moral of the story is whenever they want the first however many non-zero terms, usually solving for the derivative, the highest derivative, and then taking derivatives of that is a lot quicker than using the series solution method. The time where we have to use the series solution method is if they want a recurrence relation. If they wanted the recurrence relation so we could find the coefficients for this, what was it saying? Yeah, so if they wanted the recurrence relation so we could find the rest of the coefficients of this series, we would have to do it the series solutions way. Rachel also asked, where can we find more problems like this one? Because I couldn't find ones like this in the textbook. Well, so you could go over, so this homework is a good source of these, as is the lecture quiz. I'm not sure. Let me take a look at the textbook later and see if I can find more of those and send them out to you. You could also do a lot of, yeah, you could pretty much just do any series solution problem you want in this way, as long as you don't need the recurrence relation. So that could be good practice. You can just take any series solution problem and then just use this method for practice. But I'll try to send out some problems later. All right, let's see. So next we have homework 26, number 9. Let's take a look at that. Let's see. Homework 26. Oh, by the way, so here's another reminder. Remember that all of the assignments are due tomorrow at midnight. So make sure you have all of those completed by that time. Because after that time, anything that's left uncompleted will give you a 0. So make sure you finish up all the stuff by the end of Friday. All right, let's see. Homework 26, number 9. It also looks like number 12 is on there as well. Let's see. Okay. So find a power series for f prime, given that f of x is sine of x is the Maclaurin series for sine of x. All right, well, one obvious way we could solve the problem is, well, if f of x is sine of x, we know what f prime is going to be. It's going to be cosine of x. So we could just go to the Maclaurin series table and get cosine of x, that series, and then just use that. But let's see how that would actually happen. How would the sine series turn into the cosine series? So we have sine of x is the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Remember, sine is an odd function. That's why it only has odd terms in power series. And then for this one, let's see. Oh, we have a question about this. Will you give us one that it already has on the table, or will we have to take the derivative? It's entirely possible we could give you a function that when you take its derivative, it doesn't appear on the table. So I would definitely know how to take the derivative of the power series. But fortunately, it's not that hard to do. So if this is our function f of x, then if we want f prime, well, hopefully we're going to end up getting something for cosine. Now, the way we do a derivative of a series is all we have to do is just do the power rule. So anything that has an n in it, or just a constant or number, we leave that totally alone. But anything that has an x in it, we take the derivative of that. So what's happening here is I leave this summation alone. I leave negative 1 to the n alone. I leave my 2n plus 1 factorial alone. You see, the only thing that involves x is this x to the 2n plus 1. So what I'm going to do is I'm going to take the derivative of that by the power rule. So I bring this power down. I bring the 2n plus 1 down, and I lower this power by 1, so now it's going to be 2n. Now, this doesn't 100% look like the cosine series we have on the table, but that's because there's some cancellation we can do. If we have 2n plus 1 up here and 2n plus 1 factorial down there, 2n plus 1 factorial is 2n plus 1 times 2n minus 1. So what happens is this cancels off the first term and then factorial. so it starts one term earlier. So for that one, we're just going to end up getting cosine of x is the sum from n equals 0 to infinity, -1 to the n, x to the 2n divided by 2n factorial. And there we go. We have exactly what appears on the sheet. Oh yeah, okay, so a lot of confusion about this question is, okay, well, doing this isn't too hard, it's just doing a power rule, but why doesn't this index change? You may remember from Calc 2 that sometimes when we did a derivative, we bumped up the index by 1. So that's kind of a misconception coming from Calculus 2. The fact of the matter is, when we do a derivative or also an integral, we don't change the index of the starting index at all. The reason why some people shift it up by 1 when they do the derivative is, let's say we have some generic power series here. Sum from n equals 0 to infinity an x to the n. And let's take a derivative of this. So y prime. All right. Well, like I said, we don't need to change that, so we could just leave the summation alone. An's a constant, and then we multiply down by this n right here. We have x to the n minus 1. And this right here is totally fine. There's nothing wrong with leaving your derivative like this. Now, the reason why some people might change the starting index to go up to 1 is that if you plug in this first number 0 into here, what do you get? Well, you actually end up getting 0. So some people are like, okay, well, I don't want to bother adding in this term that's just going to be 0 anyways. Why don't I just start at the next number, which is 1? If I plug 1 in here, that's not necessarily going to be 0. So that's why some people change their starting index after a derivative. But you can only do that if your starting index would make whatever is in here be 0. If it doesn't, like in the problem we just did, we have to keep it the same. And it's the same by default anyway. So you could always just leave it as 0 if you want. All right, so there's that. Let's see. Oh, we also want to do number 12 from this one. So determine the Taylor series about the point x naught for f of x is ln of 1 plus 20x. All right, so our function is ln of 1 plus 20x, like that. Okay, now this series actually looks kind of similar to something that appears on our Maclaurin series chart. So on the Maclaurin series chart, it says that ln of 1 plus just x is the sum from, how do they write it in this one? Oh, they do 1 to infinity. And then -1 to the n plus 1, x to the n over n. There's another way where you could start this at 0, and then these are shifted by a bit, but this is fine too. So this is the series for ln of 1 plus x. But we want ln of 1 plus 20x. All we need to do for that one is just erase this x right here, meaning we also get rid of that. And in its place, we're going to put 20x instead. So we have 20x there, and then that means we're going to have 20x raised to the n as well. So that's probably one of the easiest ways to make a new power series is take an existing one and then just substitute something in that's different than the x before. Now, one thing you got to remember is this isn't just 20 times x to the n. This is 20x raised to the n, meaning that that 20 will also be raised to the n. So another way we could write this is 20 to the n times x to the n. And this is important because when you're working with series, you usually want to get the x to a power by itself because it's easier to do derivatives and integrals that way. You don't have to worry about a chain rule or use sub. So it's best to get these on its own. But anyways, that's how we find out the series for ln of 1 plus 20x, is we just do a substitution. All right, let's see. How do you get the n plus 1 in the denominator? Oh, so for the, maybe for the, oh, I see. So what they did was they shifted the index. So what they did was they lowered this one by 1 and then raised all of these by 1 as well. And that should give you something that appears in the answers there. So if we do that, we have the sum n equals 0 to infinity. Now, if I raise this by 1, -1 to the n plus 2, that's just the same thing as -1 to the n. So we can keep it like that. And this is 20 to the n plus 1, x to the n plus 1 over n plus 1 like that, and that looks like, yeah, that definitely looks like one of the choices we have on here. So they just shifted index. Oh, so -1 to the n plus 2, that is equal to -1 to the n times -1 squared, right? Because of the way exponents work. But then -1 squared is just going to be 1. So anytime you add an even number inside a -1 to the power, you can just get rid of it because there's just going to be 1. All right. So that takes care of that one. So sometimes you have to like shift the index to make sure things look like the answers here. All right, so our next set of questions is from Cam. We want to go over questions 17 and 19 from the practice exam. I already have that one pulled up. Let's take a look at those. Let's see, 17. All right. This is a good one. I'm glad someone picked this to go over. This is just kind of a subtle point here. So this one is all about determining what are called the singular points of a differential equation. Now, singular points, essentially what that means is it's going to be very hard to find a series solution about a singular point. It technically is possible, but we're not even touching that in this course. And I've done it once before, and it's like, it's really awful to do that. So it's good to identify what the singular points are so you won't have to go through, well, that horrible mess. So we have x squared minus 1 times y double prime plus 1 minus x times y prime. And then we have x squared minus 2x plus 1 times y. And that all equals 0. And so we want to determine the singular points of our system. Now, typically, what will make these be singular points are anything that makes this up here be 0 or undefined. So, well, this is going to be defined everywhere, but the points that make it 0 are when x squared minus 1 is 0, or x squared is 1, or when x is plus or minus 1. But, and that is one of the answer options, but you might be surprised if you click that one, it's actually going to say it's wrong. And there's kind of a subtle reason why that's wrong. So let's investigate that. So what we're going to do is we're going to divide everything by this x squared minus 1. Usually when we have problems like this, we want to get y double prime on its own for second order equations. So we have y double prime plus 1 minus x y prime over x squared minus 1. Now I'm also going to factor x squared minus 1. That factors into x plus 1, x minus 1. And then we have this guy right here, x squared minus 2x plus 1 times y. This polynomial factors 2. This is going to factor into x minus 1 squared. And on the bottom, we have x plus 1 times x minus 1. And that was all times y. All right, now let's see what we can do here. So technically, what makes something a singular point is making these functions undefined. But one thing you are allowed to do is you're allowed to simplify them before you check to see if they're undefined. So 1 minus x and x minus 1, those aren't exactly the same, but they are off by a negative. So what we could do is we can cancel those out as long as we put a negative sign out front. So we can get rid of this guy, change it into a 1, but now it's going to be a negative in front, and then this goes away from the bottom. So this just turns into 1 over x plus 1. And then we could also do some canceling here. We have this squared over just one copy of that. So the square goes away, and we also get rid of the x minus 1 on the bottom. Now that we've simplified these, the only point that makes these be undefined is actually -1. It turns out that all the instances where 1 would cause a problem have all canceled out when we did that. So the moral of the story is if a point makes all of them be 0, like all these polynomials will factor and give you the same thing, then that actually isn't a singular point. So it turns out only -1 is going to be the only singular point here. So that's kind of a subtlety. Don't just check to see what makes the 0. Make sure that it doesn't, whatever makes that 0 doesn't cancel out from these guys either. So that's kind of a weird one. We also had question 19 here. This is another good chance to practice our power series skills. So let's see what that is. This is another one where we're just finding the first however many non-zero terms of our series. And it looks like this time they want 4 non-zero terms. Also, this time is going to be a little less confusing because they actually give us initial conditions, so we don't need to have A naught and A1, all that stuff floating around. All right, let's see. So we have y double prime plus x minus 2y prime minus y is 0. And we have y of 0 is -3, and y prime of 0 is 0. All right, so our goal is to find the first 4 non-zero terms. All right, now remember, whatever our y naught is, or y of 0, that's going to be our a naught. And then whatever this is going to be a1. So right away, we see that we're going to have to go to at least x to the 4th to get 4 non-zero terms, because the thing next to x will be 0. So let's kind of build our polynomial as we go along. So far, based on just the initial conditions, our solution so far looks like -3, and then this is 0 times x, so we don't have a linear term. So now what we need to do is we need to figure out what a2 is, and that involves solving for y double prime. So what I'm going to do is I'm going to add this over, subtract that over. So y double prime is going to be y minus x minus 2, y prime, like that. And then I'm going to go ahead and plug in x equals 0, or whatever the center of our series is, into all this stuff. So y double prime of 0. Let's see, y of 0 we said was -3. And then we have minus, this will turn into a -2, so we have +2. But then y prime is just 0. So it turns out that y double prime of 0 will be -3. But remember, we're not looking for y double prime exactly. We're looking really for a2. And a2 will be whatever y double prime is divided by 2 factorial. So it'll be -3/2. So next, we're going to have -3/2. And then there's an x squared since it was a2. So far, we just need to remember the a2. That's going to be -3/2. All right, well, so far we have 2 non-zero terms. That means we're going to need to do at least 2 more derivatives here. But thankfully, these derivatives don't look like they're going to be so bad. Let's do another derivative to get y triple prime. We could probably get rid of this stuff now. All right, let me do it down here. Y triple prime. Let's see, so the derivative of y is y prime. And then we have a little product rule right here. So the derivative of x minus 2 is 1. So then I just have minus y prime. And then I leave the x minus 2 alone, and then take the derivative of y prime, which gives me y double prime. Now, one kind of nice thing that happens here is that the y primes end up canceling out. So we actually have those go away, which is kind of nice for the future. And then we can just plug in x equals 0. So once again, we have this -2, so it's going to be +2, and then times y double prime, which was -3. So y triple prime ends up being -6. But the thing is, remember, we're not looking for y triple prime exactly. We're looking for y triple prime divided by 3 factorial. And 3 factorial is also 6. That means that a3 will be -1. So we're continuing to build our answer here. We have minus x cubed. Let's see here. Have we uniquely identified one of these answers yet? Well, one thing about doing a multiple choice exam is sometimes you'll be able to uniquely identify an answer really early on. Like maybe only one answer has this combination of numbers so far. Then you can kind of just stop there. So that's kind of a tip for doing an exam. Unfortunately, it does look like 2 of these have this setup so far. So we do need to do one more. So I'm going to do now my 4th derivative, remembering that a3 for y triple prime was -6. All right. So now let's do the 4th derivative. But thankfully, because of that cancellation, it's still not going to be bad. Usually at this point, it gets kind of annoying writing tick marks. So I do parentheses 4 to symbolize the 4th derivative. And all I'm doing is taking the derivative of this, which is a product rule. So the derivative of x minus 2 is 1. So I have -1 times y double prime. and I have minus x minus 2, and then we have y triple prime. All right, so then let's go ahead and plug in what we have and see what this number is going to be. So here, remember, y double prime was -3, so we actually have a positive 3 there. And then we have positive 2 times y triple prime, meaning we have -12. So overall, this number ends up being -9. But remember, just like all the other ones, we're looking for that number divided by 4 factorial this time. So -9 over 4 factorial. 4 factorial is 24, but we can actually reduce that because the top and bottom are divisible by 3. It'll simplify to -3/8. We have -3/8. And there we go. So we got all of our coefficients, and that uniquely identifies an answer. We have 4 non-zeros, so we're able to figure that guy out. All right, let's see what we got here. We also have homework 26, number 13. Let's check that one out. Let's see. All right, this one's about finding a Taylor series. Now, with this one, in this problem, it's centered about a point that isn't 0. So that means we're not going to be able to use the Recurrence series table, because all of that stuff is talking about centering around 0, but this is going to be centered around 5. So let me show you what this problem is. So in this one, we want to find the first 3 non-zero terms with center 5. So there's going to be a bunch of x minus 5s for this one. And what function are we looking at? We have the function √7x, like that. Now, you could keep the function like that. One thing I'm going to do to make my life a lot easier is I'm just going to split it up as √7 times √x. That way, this is just a constant. I don't need to worry about keep doing these annoying chain rules along the way. Now, the way we get a Taylor series is we make what's called, or like I call it, a Taylor series table. So that table consists of having n, and we want to go 0, 1, 2, so we have at least 3 non-zero terms. Hopefully that'll be enough. And then the things we put in this table are the nth derivative of our function. Then we take that derivative and we plug in the center, which in this case is 5. And then finally, we take whatever number that is and divide by n factorial. So kind of like all these series solution problems, we're sort of building our coefficients by finding these derivatives. So let's see here. So the 0th derivative of something, that's just the function itself. So that's just √7x. And if I plug in 5, that'll be √7 times 5, which is √35. And then 0 factorial, that's equal to 1. So it's still just going to be √35 over here. All right, so as we're building our function, that means that so far f of x is just going to be √35. And then we're going to have some other stuff along with it. All right, now for the first derivative of this, I do the derivative of √x, meaning I do the derivative of x to the 1/2. So that's a power rule. So I have √7 over 2 √x. So remember, the √7 was a constant. I multiplied by 1/2, lowered the power to be -1/2. Then I plug 5 into that. I have √7 over 2 √5. And then dividing by 1 factorial, that's still just going to be the same number. It's still 1. So I'm going to write the same number. Now, I think if I'm looking at the answers here, it seems like they get the square roots out of the denominator. And the way they do that is they multiply the top and bottom by √5. So I'm just going to do that now so it matches up with our answers here. So if I multiply the top and bottom by √5, I have √35 up here. And then √5 times √5 will be just 5, and then times 2 will be 10. So my next coefficient is going to be √35 over 10. So √35 over 10, and then notice I have times x minus 5. Don't forget to put minus whatever the center is. It's not just x, it's x minus center. All right, and then we have just one more of these to do. We're going to take another derivative of this. That'll be -√7 over 4. times x to the 3/2 down there. So I did another power rule. I'm going to plug 5 in for that. So I have negative root 7 over 4 times 5 raised to the 3/2 power. And then just like the other one, it seems like they decided to rationalize the denominator here. So I'm going to multiply the top and bottom by root 5 again. So on the top, we have negative root 35. Now remember, in this case, we have n equals 2. So in addition to doing the rationalizing part, I also need to divide by 2 factorial. Dividing this by 2 factorial will turn this 4 into an 8. That's going to turn into an 8. And then multiplying by root 5 down there to do that rationalizing, that's going to turn this into 5 squared, or 25. So that's just some algebra there. I multiply the top and bottom by root 5, and then I also divided by 2, since I need to divide by n factorial. So if I multiply all this out, that means my final coefficient is going to end up being negative root 35 over 200. So we have x minus 5 squared. And then we have 3 non-zero terms, so we could definitely stop there. So in a nutshell, this is how we make Taylor series centered about points that aren't 0. We unfortunately can't use the table, but we could just make a derivative table kind of like this and then make our own coefficients for it. So that's how we deal with that. Let's see, let's scroll back a bit. Okay, I think I already answered these questions. Anika asks, do we have to remember how to do the limit comparison and alternating series test? I would say for sure you should know how to do the alternating series test. When checking endpoints, that one does show up fairly often. So I would certainly review that if you're feeling rusty. Limit comparison, technically you're using that behind the scenes, but at this stage, you're usually kind of limit comparing things to a p-test. So for example, let's say for an endpoint, let's say you were checking out an endpoint and you had this series. Let's say we had the sum from 1 to infinity, 1 over like n squared plus 7n or something like that. So if we were back in Calc 2 and we were trying to write everything out, this would technically be a limit comparison, and we would limit compare it with 1 over n squared. But now, since that's kind of in the past and we want to just kind of get through this stuff, we notice that the leading power on the bottom is going to be n squared, and the leading power on the top is still just 1. So this is going to act a lot like 1 over n squared. And if we remember the p-test, 1 over n squared is going to converge. So technically, in order to do that rigorously, we would do the limit comparison behind the scenes. And if you're not comfortable with it, I do suggest doing that. But if you kind of see what the leading things on the top and bottom are doing, then you could usually tell whether the series is going to converge or not. So I would say more focus on alternating series tests and also understand the p-test, or looking at the dominant terms on the top and bottom. That would be what I would say would be important, besides obviously the ratio test. The ratio test is the main one, but also take a look at those. One other thing is keep in mind also the test for divergence. It's really easy to forget about, but it helps when you have a series that looks like -1 to the n or something like that. That's just test for divergence is going to diverge. And you do see series like that sometimes. So be sure to keep that in mind as well. All right, the next question is homework 27, number 2. Let me pull that up here. 27. And number 2. Okay, so there's no way around this one. This one we have to find a recurrence relation because that's what they asked for. Actually, there's actually a mistake in this problem, which I'm going to fix later today. Technically, they use the recurrence relation at an n value that they shouldn't be using it at. But I'll explain that as I do the problem. So this problem's a little bit messed up right now on the computer, but I'll explain what's happening. All right, so this one we have to make the recurrence relation for, so we're going to use series. So we have x squared plus 1 y prime plus y is 0. So this is only a first order equation. And so we're going to do a series solution for this. So as always, the series solution is going to look like y is the sum of a n x to the n. And as it happens with those, oh, actually, before I do any of that, I'm going to FOIL this out. There we go. So now we have each term separate, and that's pretty important to the series. So y prime, that's always going to look the same every time. That's the sum from 1 to infinity. But remember, you could also do 0 as well. N, A, N, x to the n minus 1. And then we have y prime without an x squared in front, which looks the same on the inside. And then we just have a regular old y, which is the sum from 0 to infinity, a n x to the n. And adding all that stuff together should give me 0. So that's kind of a setup for our series problem. Now, when we want to do the recurrence relation, we have 2 goals before we can get there. We need to get all of the x to the powers to be n specifically. So that requires some reindexing. And then we also need to get all of the series to start at the same number. So we always start by getting everything to be the nth power first. Now, if I multiply this x squared in there, what happens is that I get 2 more x's, so this n minus 1 becomes an n plus 1 instead. And what that means is that I'm going to need to lower everything in here by 1, and consequently, I need to raise the starting index of that by 1. So my next stage here, I'm going to have the series from n equals 2 to infinity. Then I lower these by 1, so I have n minus 1, a sub n, x to the n. Then my next series, it has the opposite problem. The power is too low. So I need to raise these ones by 1 and then lower that one by 1. So now this one starts at 0. And then I have n plus 1, a sub n plus 1. Oh, I forgot to make this a sub n minus 1 over here. Don't forget to also subtract from the a. And then we have x. And then this one is already just right here. We have n equals 0 to infinity, a n x to the n. That one's already good. Okay. Next, what we need to do is we need to make sure all of these start at the same index. Now, if we look here, it seems like usually we try to get it to match up with the highest index. So normally we would try to turn these guys into 2's. But one way we can save ourselves some work here is by changing this index to be 1. And why can we do that? Why can we just arbitrarily change that to be a 1? Well, what happens if we plug 1 into here? We have 1 minus 1, that will be 0. So by including the n equals 1 term, I'm pretty much just adding in 0, but as always, adding in 0 doesn't change anything. So it's okay to start this one at 1. Now, sometimes I'd like to get a little bit greedy and start it at 0, because then I'd already be done. But if I plug in n equals 0, that's not going to be 0 in there, so I can't do that. So now, at least I made it easier on myself, because now all of these guys, I can just make them start at 1. And the way I do that is I plug in the n equals 0 term, and I just move those out to the front of all the series. And then those are called the dangling terms, because they're not part of a series anymore. So I plug in n equals 0 here. I have 1a1, and then that's it. So it's just a1. Now that one can start at 1. And then I plug in 0 here, and it looks like I have a0 for that. So I have a1 plus a0. And then now the rest of the stuff starts at 1, because I moved out the 0 terms from here. So now I could write everything in one giant series here. So I have n minus 1, a sub n minus 1, plus n plus 1, a sub n plus 1, plus a sub n. Remember, all of that is times x to the n. That's why we bothered to do that, so we can pull the x to the n out. And all this is still going to add up to be 0. So now that we have this, we can end up writing our recurrence relation. So what we do is we take all this giant coefficient right here, and since this power series needs to be identically 0, it needs to be the 0 power series, all of those coefficients have to be 0. So we just take n minus 1, a sub n minus 1, and then we have the n plus 1 version, and an, and all that stuff needs to be 0. And so it's customary with these recurrence relations to solve for the highest index a value. I'm going to solve for this an here. So I have n plus 1, a sub n plus 1 is negative an minus n minus 1, a n minus 1. And then finally, I just divide everything by n plus 1. So I have a sub n plus 1 is negative an minus n minus 1, an minus 1, divided by n plus 1. And note that this is valid for n greater than or equal to 1. The recurrence relation is only valid from the starting index of the series. So since the series this came from started at 1, it's only going to be valid for n greater than or equal to 1. And let's see, hopefully this matches one of the answers here. Oh yeah, it does if you factor out the negative here. So that negative goes to the outside, and then we have this. Okay, so that's going to be our recurrence relation. And then what we're going to do is we're going to use that to determine the first 4 non-zero terms. Well, as with all of these problems, we actually end up already having some of the terms to begin with. So since this is a first order equation, we know that y of 0 is going to be a0. So far, our y is going to be a0, and then we have 1. It's always going to be that if they don't specify an initial condition, which they did in this time. But one thing we had, I erased it a little bit ago, but we actually had something in our series that told us what a1 was going to be. We had a0 plus a1, and that term also has to be 0 as well. So all the dangling terms need to add up to be 0 too. So it turns out that a1 is just going to be the negative of whatever a naught is. So what we could do is we could just put that in here, have a negative 1, and then since it's the a1 term, we put an x next to it. So if we were on a real exam, that would be it, because there's only one answer that has only a naught in it. So we immediately know it's going to be that one. But if we were to continue on doing this, to get a2, now we can start using this recurrence relation. So now I could plug in n equals 1 here and get that a2 is negative a1. Well, 1 minus 1 will be 0, so we won't have that. And we divide by 2. So a2 is negative a1 over 2, but then that means that a2 is just positive a0. That means we're going to have plus 1/2 x squared right there. Now this is a little bit confusing. So with all the other series problems, we needed to remember to divide by the factorial. But if the one advantage of doing it the recurrence relation way is that you already solved for your a whatever number. You don't need to divide by another factorial. So whatever number you get for this is exactly the number you're going to put there. So don't divide by an extra factorial. And then finally, it looks like if I plug in n equals 2 here, I'll end up getting some constant for a3. Hopefully to match up with the answer ends up being x2 over 6. I thought there was an issue with this problem. Maybe the last time I tried it, I made a mistake. All right, it seems okay now, I guess. Sorry about that. But yeah, so that's how we do that one. That one we need to define a recurrence relation. All right. All right, next we have a question from Anika about homework 26, number 5. But let me answer your second question real quick. When we take the derivative of y, y prime, y double prime with respect to x, do we need to use the product rule? And the answer is yes. So the way we would do that, let's say we wanted to do the derivative of y, y prime, y double prime, and this happens often if you're using the differentiation method of solving these power series problems. You may need to deal with product rules like this. All right, so for this one, we could use what I like to call the triple product rule, where we kind of take turns between all 3 terms as we're going. So first I'm going to take the derivative of y and get y prime, but then combined with this other y prime means I have y prime squared, and then we have y double prime. So I took the derivative of this guy. Next, I'm going to leave this y alone and take the derivative of y prime. And that's y double prime, but I already have one of those, so that'll be y double prime squared. And then for the final one, we have y prime, and then I take the derivative of y double prime to get y triple prime. So that'd be how we would deal with the product rule in that case. Oh yeah, you also asked when we do the recurrence relationship, we don't need to think about the factorials. That's right, yeah. So that's an advantage of that method because an already kind of includes the factorial already, so you don't need to divide by anything extra for that. All right, so that was that question real quick. Let me go to lesson 26, number 5. Okay. Determine the interval of convergence for this series. All right, what series is this? Let's see. So this is the sum from k equals 0 to infinity of 2 to the 2k x to the 2k. All right. Now, when we're doing the interval of convergence and radius of convergence, the first thing we always need to do is the ratio test. We're going to do the ratio test first to at least establish what the main part of the interval is. And then at the end, we may need to check endpoints if it's not an infinite interval of convergence. So let's do our limit as k goes to infinity. Now, typically, these are fractions, but actually, this one isn't a fraction. So I can kind of just write this all in one go. I plug in k plus 1s for these, but this is a very common pitfall in Calc 2. Remember that if you put k plus 1 here, you need to distribute the 2 all the way through it. So the top will be 2 to the 2k plus 2. And the same thing will happen with this x term. And then on the bottom, we just have 2 to the 2k x to the 2k. All right, and then once we get to this point, then comes the simplifying. And notice this is pretty easy simplifying. The top just has 2 more powers than the bottom one. So that goes away, and that entirely goes away. And the same thing happens with the x term. So what are we left with? We have the limit as k goes to infinity, 2 squared, or 4 times x squared. And we can actually get rid of the absolute values because, of course, x squared is always positive. So really, we just have 4x squared. Now, what's the limit as k goes to infinity of this? Well, it's sort of a silly question because we don't even have k anymore. We've already canceled it all out in the canceling there. So whenever we don't have the variable in question for the limit, we can just get rid of the limit. So this is just equal to 4x squared. And remember, whatever we get out of the ratio test after the limit needs to be less than 1. Or less than 1 right there. So now we just need to solve this inequality to see what x values make that happen. I'm going to keep this up, actually. I'm going to keep up the series. OK, so the way this is going to work, the way we deal with this, we have 4x squared less than 1. First thing we could do is divide by a 4. X squared is less than 1/4. Now, the way we do deal with squares and inequalities, it's kind of similar to the way we deal with absolute values. What we do is we take the square root of both of these. So we're going to have x and 1/2. But the catch is we need to put a negative version of the square root of this on the other side. So this means that negative 1/2 is less than x is less than positive 1/2. So we at least know the interval of convergence is going to go from negative 1/2 to 1/2. But as always, the question is, does it include the endpoints? Because the endpoints give 1 for the ratio test, and that's inconclusive. We usually just check those manually by putting them into the series. So how about we start off with x equals 1/2. Let's plug that into our original series and see if that converges. So when we do that, we get k is 0 to infinity, 2 to the 2k, and then 1/2 to the 2k. Now, when we have the same powers, we can multiply the things being raised to those powers, but 2 times 1/2 is going to be 1. So this is going to be k equals 0 to infinity of 1 to the 2k, but really 1 to any power is just going to be 1. Okay, so we're just looking at the summation of 1, and that's certainly going to diverge because we're just adding up together infinitely many 1s. If you want a test to do that, that's the test for divergence. This guy doesn't even go to 0, so there's no chance it can converge. So that means it diverges. So that means we're going to stick with this kind of open inequality right there. And then now let's check negative 1/2. But I think the same thing will probably end up happening for that. So if we check negative 1/2, well, then we have the sum from k equals 0 to infinity, 2 to the 2k, negative 1/2 to the 2k. Now, first of all, we're raising a negative to an even power. So the negative's going to cancel out no matter what. So I might as well just erase it here. And then once we do that, then we see, oh, wait, it's exactly the same as what we had earlier. So we know that that's going to diverge as well. So it turns out that this series doesn't include either endpoint for its interval of convergence. So we would just pick the one with 2 parentheses at the end of that. All right. So let's see here. And then we also want to check the endpoints for 26, number 4. So that's the previous question. All right, so let's write out what that series is. All right, so this one is the sum from n equals 1 to infinity of 10. And then we have x minus 4 to the n divided by n squared plus 7n. I think this is where I thought of my example earlier. So this is a good time to practice that. So what we're going to do is we're going to plug in the endpoints. So the endpoints for this one are going to be 3 and 5. So we automatically, well, we would know from doing the ratio test that it's certainly going to be from 3 to 5, but do we include 3 and 5? So I'm going to plug 3 into here and see what happens. All right, let's get rid of this now. So if I plug 3 into here, I have n is 1 to infinity, 10. Now 3 minus 4 will end up being negative 1. So this will be negative 1 to the n over n squared plus 7n. Now this is a good time to practice our alternating series test, because this is definitely going to be an alternating series. Now alternating series are really easy to look at and understand if they converge or not, because all you have to do is look at the part that isn't alternating like that, and you just see if, well, first of all, it needs to be monotonically decreasing eventually. That almost always happens. But you also need to check to see if it goes to 0. And as n goes to infinity, this bottom's going to get really huge, and this will go to 0. So this converges by the alternating series test. So we actually will end up including 3 as an endpoint. So far, it's at least going to include 3. Now, let's see if it includes 5 as well. So for 5, this time I'm going to plug in 5 in there. And I have 10. Now, 5 minus 4 will just be 1. And then 1 to the end, doesn't matter what n is. Still just going to be 1. So this is going to simplify down to n squared plus 7n. And this was exactly the thing I was talking about earlier. So technically what we would do for this one is we would do a limit comparison test with 1 over n squared, because that's what it's going to behave like. But in the interest of time, we can kind of just see that the dominant term up here is a constant. The dominant term down there is a square. And as long as this power is more than 1 greater than whatever that power is, which is 0, it's going to converge. And so we would limit compare this to 1 over n squared, and then say 1 over n squared converges by the p-test. So this is going to converge too. But at this point, you can kind of be fast and loose with it and be like, okay, this is 2 powers greater than that. That's more than 1. So it's going to converge. So you can kind of think of it as like a p-test, but technically you're doing a limit comparison, or maybe direct comparison behind the scenes. Well, the moral of the story is this will converge too. So this is an instance where we include both of the endpoints. So it would be square brackets and then include 3 to 5. Now sometimes, so we had an example where we didn't include either, example where we included both. There's sometimes where we include one side but then not the other. That can happen as well. So be on the lookout for those. All right, looks like JT answered Anika's question. We'll have 22 questions, that's right. And then what is the time window to take the exam? So you can start the exam as early as, I'm actually going to make it 8 a.m. There's this one student who needs to take it early, so I might as well just take it. I mean, if you really want to wake up at 8 a.m., take it. Yeah, I'm not going to stop you. So you can take it 8 a.m. And then the latest you want to begin to get the full 2.5 hours would be 9 p.m. because the exam closes at 11:30. So you can technically start after 9, but you're starting to come into your exam time if you do that. So you can start as early as 8 a.m. and start as late as 9 p.m. and get the full time. So that's the time window. All right, let's see here. I probably have time for one more question. It looks like we do have one more question. Lecture 23, number 12. So let me pull that up real quick. Let's see here. Lecture 23, number 12. Okay, so this is back in the Laplace transform section, and this one is about solving an integral equation. So even though this class is technically differential equations, they're really closely related to integral equations. So it's also nice to look at those too. So we have y prime, let me make that look more like y prime. Y prime minus 8 times the integral from 0 to t of e to the 2 times t minus v, y of v dv. All that stuff is going to equal 3t. And they also give us the initial condition that y of 0 is equal to 5. Okay, so how are we going to solve this one? Well, it's in the Laplace transform section, so we should probably use the Laplace transform. So I'm going to take the Laplace transform of both sides of this. Another massive hint is that this integral might look familiar. This is a convolution integral. And this is actually the convolution of e to the 2t convolved with y of t. And remember, convolutions work super nicely with Laplace transforms. So if I take the Laplace transform of y prime, that'll be s times Laplace of y minus whatever y0 is. So it's going to be minus 5 in this case. Then we have minus 8. Now, if I take the Laplace transform of a convolution integral, the nice thing that happens is I just do the Laplace transform of this times the Laplace transform of that. You can almost kind of think of it as like a product rule, but for Laplace transforms. So that's going to be the next thing I'm going to do here. So Laplace transform of e to the 2t will be 1 over s minus 2. And then Laplace of y will just be this capital Y. We have that. And then finally over here, Laplace of 3t, if we look on the table, will be 3 over s squared. All right, great. So we have our Laplace transform all set up. So now what we're going to do is we're just going to solve for capital Y here and then transform back into something that involves t. So the thing I like to do, and the thing that unfortunately kind of happens with these convolution problems, is you often end up with a fraction over here. So I'm just going to multiply both sides by s minus 2. So we can just get rid of that. So I have s times s minus 2y minus 5 times s minus 2 minus 8y is 3 times s minus 2 over s squared. Okay, so we were able to get that. All right, and then now on this left side, I'm going to factor out things to get my, I'm going to factor out my y. So if I multiply this out, I have s squared minus 2s. Then I have this negative 8 right there times y. And then I'm going to add this 5s minus 2 to the other side. So I have 5s minus 2 over there. And I still have this 3s minus 2 divided by s squared. And then finally, I'm just going to go ahead and divide both sides by this. So we get the capital Y. And actually, as I'm dividing this, I notice that this is one that I could factor. This is going to factor in s minus 4 times s plus 2. Kind of wish it was s minus 2 so we could cancel, but it's not that lucky. So we have 5s minus 2 over s minus 4, s plus 2. And then we have 3s minus 2, and then we have s squared, s minus 4, s plus 2. All right, so there we go. So we isolated our Laplace transform of y, and then now we just need to transform back. And unfortunately, I don't have enough time to do that. I'll kind of briefly explain how we would do that. Both of these are something that can be split up by doing partial fractions. So I would do partial fractions on this one, And unfortunately, we need to do a separate partial fractions on this one because it has an s squared at the bottom. Actually, one way around that is you can multiply the top and bottom of this by s squared and then combine them all together. It'll be one partial fraction that'll be a bit tougher than either of these two, but it might save time because you only have to do one. So either way is up to you. You're definitely going to have to do partial fractions with this, and then this should just turn into a bunch of exponentials, hopefully, if it goes well. So the rest of this is just partial fractions. So hopefully that's okay. Looks like Anika has one final question. Would the exam have the dampening question, like if it's over, under, or undamped? Yeah, so that definitely could be on there. So make sure you understand the difference between the several types of dampening. There are 4 types of dampening: undamped, underdamped, overdamped, and then critically damped. And they all depend on the value of b, or the dampening constant in the equation, and whether b squared is greater than or less than or equal to 4mk. So that's what that depends on. All right, guys, it looks like I'm out of time, but as always, you can feel free to email me any questions you have, and I'll be happy to answer them. And I wish you guys all the best of luck on this final and then any other finals and projects you guys have. So yeah, best of luck on all that stuff, and I'll see you guys later.